So the main goal is, given any matrix, the idea is to come up with a sequence of row operations that will actually turn it into row echelon form, or if you're particularly ambitious, to turn it into reduced row echelon form. So I'm going to show you how to do that in just a moment, but before we get to that, I need to introduce a little bit more terminology. So the first one is, if you have two matrices, let's call them A and B for the purpose of this conversation. So that's why we start with two matrices, A and B. Those matrices are said to be row equivalent if you can turn one of them into the other just by performing a sequence of elementary row operations. So, and it's a two-way street, right? If A is row equivalent to B, then B is automatically row equivalent to A. So it's a two-way street. So now let's say you have a matrix A and you want to turn it into row echelon form. Well, once you've done that, what you have now is the row echelon form of that matrix. So let me just rephrase this formally now. So if you start with a matrix A and you perform row operations on it until it is in row echelon form, then let's give that result a new name, because you would have changed the matrix by that point. And let's say you call that new matrix R. Well, then R is called a row echelon form of A. And notice I said a row echelon form of A, not the row echelon form of A. The idea is there's many different ways to turn a matrix into row echelon form, and the result may look different depending on what your choice of row operations are. For example, if you start with a matrix and I start with the same matrix and we both do separate row operations, that we go into different rooms so we can't see what each other are doing, and we both turn our matrix into row echelon form, we may have done different steps and we may have different results, but they might still both be row echelon forms of the matrix A. So there's possibly many different ways to do it. But the neat thing about reduced row echelon form is that there is only one reduced row echelon form of any matrix. So if you have a matrix A and you do row operations to turn it into reduced row echelon form, then what you have, in this terminology definition here, the result is nicknamed R, then R is called the reduced row echelon form of A. And I safely can use the word the here because of this next remark, and that is the reduced row echelon form of any matrix is unique. So back to the previous imaginary example, let's say you and I both have a matrix and we go into separate rooms and we do a sequence of elementary row operations that turns that matrix into reduced row echelon form. As long as neither of us did anything illegal or make any errors, we both are guaranteed to get the same result. There's only one reduced row echelon form of any matrix. So, and that's what we're actually after. When you're given an augmented matrix of a linear system, what you actually want to do is you want to turn it into a reduced row echelon form. Or in some cases, you may be satisfied just to go to row echelon form. But that's just generally what our goal is. Our goal is to turn matrices into row echelon form or reduced row echelon form. So one more little introduction of terminology, and then we'll get into the procedure that you can actually use to accomplish that. So let's start with, let's say we've got the following. We've got some matrix, and I'm not going to actually write out a matrix just yet because this applies in general, not just to a specific matrix, but this applies to any matrix A. And let's also say you've got some row echelon form of that matrix, and we'll call that R. Okay, so you've got a matrix A, you did some row operations, the result is in row echelon form, call the result R. So the positions of A that correspond to the leading entries in R are called the pivot positions. Okay, so that's what the pivot positions are. And like with other terminology, once we see an example, it will clarify any misconceptions that you may have just by hearing that definition. So if you go to the matrix R, you look at where the leading entries are, go back and highlight those corresponding positions in the original matrix A, and those are called the pivot positions of A. Now, some of the rows are going to contain those pivot positions, and those are called pivot rows. And similarly, some of the columns are going to contain those pivot positions, and those are called pivot columns. Okay, but it won't necessarily be all of the rows. It might be, but it won't necessarily be. And similarly, it won't necessarily be all of the columns, but in some cases it will be. Okay, here's an example. We've got a 3x5 matrix. Okay, and so in the context of the previous terminology, you should think of this matrix here as your A matrix. Okay, so we've got a matrix. It's not in row echelon form. and it's not in reduced row echelon form because it's obviously if it's not in row echelon form, it can't be in reduced row echelon form. Why is it not in row echelon form? Well, all the rows of zeros are at the bottom in the sense that there are no zeros, but it's not in row echelon form because it actually fails the second condition, the staircase condition, if you will. The leading entries don't follow a staircase format in the downwards to the right direction. In particular, you've got a leading entry right here that is directly below another leading entry right here. But we can fix that with an elementary row operation. We can take the first row and subtract it from, actually let's start over down here. That's typically what you will do. So I'll write out a fresh copy of this matrix. And what we'll do is we'll do the row operation that I just said. Okay, so what we're going to do is we're going to take row 1 and subtract it. Or what I'll take row 3 as the row will change, and we'll replace that with row 3 minus 3 times row 1. So we're doing our subtract row 1 from row 3 times. Okay, what's the result going to be? Well, the result is going to be, well, the first 2 rows won't change. Let's just copy them down. But then the third row will change. So what's going to happen to the third row? Well, we'll have 3 minus 3 is 0. 0 minus 0. Then it'll be 15 minus 15, which is 0 again. Then we'll have 8 minus 6, which gives us 2. And then we'll have 29 minus 21, which will be 8. And actually, you can check now that this result is in row echelon form because all the rows of zeros are at the bottom, right? There's no rows of zeros, so that the first condition is automatically satisfied. The second condition is satisfied because if you look at where the leading entries are in each row, they follow the downward staircase form as necessary. So that is in row echelon form. And moreover, the entries below the leading entries are all equal to 0. The ones that I highlighted, those are the only entries that appear below leading entries. So this is actually in row echelon form. Let me just add an annotation to reflect that. So this is like your matrix R in the previous, not the example, but the terminology. Let me just show you what I mean. So you've got I'll erase this. You've got a matrix A. That's like this matrix here. And you've got also a matrix R, which is a row echelon form of the matrix A. Well, that is like this matrix here. Okay, so that's how things match up in the terminology. So let's identify the pivot positions, the pivot rows, and the pivot columns of this matrix we were given. Okay, notice I didn't actually call this matrix A. That it doesn't have to always be called A, but just when you were stating this terminology, we had to call it something, so we chose the letter A. But okay, I'm going to erase these highlighting now so they don't get in the way. But okay, well, we want to identify the pivot positions. What are the pivot positions? The pivot positions are just the locations of the leading entries. But in particular, I'm just going to erase this while I'm talking. They're the positions of the matrix A that correspond to the leading entries of the row echelon form of the matrix A. So we know where the leading entries are. There's one right here. I'll use a different color to highlight with. There's one right here. There's one right here. And there's one right here. So that means the pivot positions, you can see I got another copy of A down here so we can just annotate it to show that we found where everything is. So the corresponding positions of the original matrix is going to be this entry, and this entry. Okay, so those are your pivot positions. So I'm just going to jot this down, pivot positions, and maybe I'll just draw some arrows that point to those entries. You're not concerned with the actual entries so much as you are concerned with the positions of the entries. So for example, this one is in the first row, the first column. This is in the second row, second column, and this is in the third row, fourth column. Okay, so what about I'll use a different color so things don't get mixed up. What about the pivot rows? Well, it looks like every row is a pivot row because if we look at the row echelon form over here, every row has a leading entry. Or if you want to just look down here, we've already identified the pivot positions. Every row contains a pivot position. So the pivot rows are actually, we'll just draw an arrow pointing to all of them. They're all pivot rows. And then lastly, pivot columns. I'll just change colors again because I can. We got a pivot column here because that column has a pivot position. we've got another pivot column here because that column has a pivot position. And then you've got another pivot column over here. So columns 1, 2, and 4 are pivot columns, and rows 1, 2, and 3 are your pivot rows. So let's just finish this off. So this is the pivot columns, and that kind of summarizes our final answer in the sense that it does what the example asks. So let's just highlight our final answer like that with a red box, and that concludes that example. So next, here on the next page, you can see this is where we actually talk about the Gauss-Jordan elimination method. So that's where we're actually going to finally see a systematic process that you can use to actually come up with a sequence of row operations to turn any matrix into not only its row echelon form, one of its row echelon forms, but also its reduced row echelon form if you so desire.